I'm going to continue with the topic of this morning, and I'm going to present some of our recent observational results on the evolution of massive galaxies, and in particular, what is the relation between their structural properties and the quenching of star formation. And to do that, I'm going to build up in some of our previous work that I presented in previous editions of this workshop, where we explore this relation between the structure and quenching to try to find the immediate star-forming progenitors of the red nuggets, these massive quench-quiescent galaxies at redshift 2. So our goal today was trying to extend this search for the immediate progenitors of quiescent galaxies since redshift 3. So try to extend this search to all redshifts and see if the techniques that we use at redshift 2 can be extended efficiently. So this is our key result. Avishai already showed a figure similar to this. So this summarizes our search for the immediate progenitors of quiescent galaxies at redshift 2. And here you can see the postage stamps of massive galaxies at redshift 2 to 3. Here in the y-axis you have the specific star formation rate, and here you have a sort of mass surface density. And this diagram is built from these two on the side here. Up you have the main sequence, star formation rate versus mass. You have this dividing line in a specific star formation rate. You have star formers and quiescent galaxies here. So in this diagram above you have all the star forming galaxies. Below you have quiescent galaxies. And now in the x-axis you go to the mass size diagram here. And we use this dividing line that essentially follows the mass size relation of quiescent galaxies. So below this line, essentially, you have galaxies with high surface density, high mass density. So all of these galaxies below here we call compact. They have high surface density similar to the density of quiescent galaxies at that redshift. And above you have this diffuse, low density, extended star-forming galaxies. And when you put these galaxies in this delta-delta diagram with respect to these dividing lines, what you see is that star-forming galaxies are above here, and here you have compact galaxies. And this arrow already indicates the presumed evolutionary sequence that goes from extended star-forming galaxies to compact star-forming galaxies, which are the immediate progenitors of these quench galaxies. And already this part is quite compelling. You can see that this subfamily of star-forming galaxies that lie in the main sequence of star formation are below the sequence that other star-forming galaxies describe in size, already have spherical shapes, they have high Sarsic index, and they really look like the quiescent galaxies. They're even red, but not because they are quenched, it's because they are dusty. They're strongly obscure, high star formation galaxies that look very different from the other star-forming galaxies. So Avishai already talked a little bit about how different mechanisms could transform these extended galaxies into more compact star-forming galaxies, and I won't go into that. Just when I saw this quick summary that we published also in our paper in 2014, where you can see evolutionary tracks for these same simulations that Avishai showed. They go from a phase A, so in orange here, where they look kind of disky, to this compact phase after this compaction event that gives you a more concentrated look. So, as I said at the beginning, our goal is to search for the immediate progenitors of quiescent galaxies at every redshift, and we wanted to use a similar diagram to the one that I showed before, and I apologize that I flipped the axis. The y-axis here is reversed. That's how we do it in the first paper. But it's the same idea. You have the L shape, you have the quiescent galaxies, the compact star-forming galaxies, and the extended star-forming galaxies here. And what I want to highlight here is this contour in black that is the same diagram at redshift 0. And you can see that the diagram moves substantially from the relation at redshift 2. So if you use a vertical line, for example, here, you use a threshold in density to select compact galaxies. Avishai already showed that as well. You run out of galaxies at redshift 0, so you don't have anything here to select. So the diagram also moves up, and that is something that you can correct simply because this is essentially showing you that the 0 point, the normalization of the main sequence or the specific star formation rate moves down with time, so galaxies become less star forming. But the other problem, the one that depletes this region here, is that galaxies grow in size. And this is an intrinsic limitation of the surface density that we're using that depends on the effective radius. So because galaxies grow in mass, you can see an example here, both quiescent and star forming grow in mass and size, you don't have a density that is defined within a given aperture. So galaxies can do both things, grow in mass and grow in size. So this density essentially moves to the left, and you don't really know what is happening. So you can, in principle, move this line to the left following the evolution of this normalization in the sizes of galaxies, but you can try to come up with a new method, try to find a more fundamental property that evolves more slowly with time. And in fact, people have been doing this for a long time. There have been many previous works before that showed that the central density of galaxies within the 1 kpc behaves better, and for example, for quiescent galaxies, it's been shown to evolve very little. So we can try to have a look at this property of galaxies, and here I'm showing you this result from Fang et al. That shows the relation between the density within the central 1 kpc, the core of the galaxy, versus the stellar mass. And you can see that just like happened in the mass size relation, quiescent galaxies follow a very tight correlation. But in this case, the scatter is very small compared to the scatter in the mass size relation. So this is a much tighter relation. You can see that also star-forming galaxies follow a sequence here. But in general, just like happened in the mass size relation, star-forming galaxies tend to be less dense, even in the central 1 kpc than quiescent galaxies. So quiescent galaxies in general have denser cores and follow much tighter relations in this diagram. So we can go back and try to construct this L-shaped diagram, but using the distance from this sequence that is tighter and presumably will evolve slowly with time. So to do that, first we wanted to have a look at this relation as a function of time to see how it behaves. And here I'm showing you just our results since redshift 3 from the Candles Good South sample. And this is the evolution of the same diagram, sigma 1 versus mass, since redshift 3 to redshift 0.5. And at the first look, you can see that the diagrams look very similar to the one at redshift 0. The same behavior was already in place since redshift 3. You can go ahead and also fit lines, just like the one that Jerome showed in 2013. And you can see that the slope is very well preserved. Essentially, it changed very little with time. The scatter is also well preserved. And the normalization of this line, especially for quiescent galaxies, this is the line at redshift 3, and this is the line at redshift 0. The dashed line here is the same line as here. You can see that this normalization evolves very slowly. It's just like a factor of 2 compared to the well-known factor of 10 in size evolution for quiescent galaxies. So this line for quiescent galaxies, but also for star-forming galaxies, evolves very little with time. So it's a quantity that is well-behaved, and it's better to perform a selection of sample. In fact, I'm going to go ahead and say that since this line evolves very little, you can actually say that the evolution of star-forming galaxies will follow along this line in a sort of structural main sequence that is similar to the star-forming main sequence. But instead of star formation here, you have the structural properties, in this case, the density within the central 1 kpc. So galaxies, with time, will follow along this line. They will grow in the total mass. They will grow in the central density. And essentially, this describes the growth, the insider growth of a disk. So the disk will increase its mass, will increase its size, but it will also increase the central density just following along this line. So galaxies on the main sequence can also follow a structural sequence in which they essentially grow inside out and gives you this evolution from a slightly disturbed small disk to something more settled with a larger size in the disk and also a central density that is higher. But still, you have a problem that in the last days of its life, these disks, when they turn into quiescent galaxies, they will have to have a higher central density than they have in the star-forming phase. So you still need another mechanism, another phase that moves galaxies from this structural sequence up into the relation of quiescent galaxies. So very similar in essence to what Avishai was mentioning, you can have a compaction phase, which in this case, for the observational data that we have here, is just a phase in which the central density of the galaxy increases faster than it does in the main sequence. So it's a phase of increased core growth where the profile of the galaxy will become steeper because you're actually adding more stars to the center. It will increase the effective density as well, and it will decrease the effective radius in some cases. So you can see also the same diagram color-coded by Sersic index and showing only the star-forming galaxies. And you can see that the star-forming galaxies that are already up there close to the mass, close to the relation of the quiescent galaxies have denser cores, and the whole mass profile is different. So the Sersic increases. So the galaxies here and here at the same mass, they don't have the same profile. They're different galaxies. Something is changed substantially. So they're just not scaled up in density disks. The center and the whole profile of the galaxy has changed. We can test this scenario comparing to evolutionary tracks in the simulations, very similar to the ones that Avishai showed. And here you can see the blue contour, the red contour here, and the lines indicate the observed relations at redshift 2 and redshift 1. And here, for example, the green track shows the evolutionary path of one of these low-mass galaxies. And you can see that this green galaxy evolves pretty much down to redshift 1 along this sequence. This is structural main sequence. And in fact, if you have a look at this galaxy as a perfectly nice disk, growing in size, growing in the central density, and in the star indicates here a compaction phase, exactly like the ones that Avishai described. In this phase, the galaxy grows its core faster, and it goes closer to the quiescent relation. And here in gray is a similar thing, but this is a stack of all the low-mass galaxies in the sample of the simulations. And you can see that high redshift, they follow this main sequence, the structural sequence developing their disk, and they have a compaction around this mass, a phase of substantial core growth. They recover, and then they continue along growing. And as I say, they have a downsizing effect. So if you look at the most massive galaxies in the sample, they actually have a compaction earlier. They depart from this structural main sequence, have a longer and a long duration compaction phase that takes you straight up into the quiescent relation. So these galaxies actually don't grow a lot in size before having the compaction event. So they're in some sort small from the very beginning. They don't have to collapse a large disk of gas. So these galaxies will be similar to the growth of a bulge inside a disk that is already well formed. And these galaxies will collapse very early on and give you these naked cores, these compact star-forming galaxies that you see at redshift 2. Okay, so going back to my original goal, I can take the main sequence in star formation as a function of time and use this distance from the main sequence to create this y-axis that I have in the L-shaped diagram before. And now instead of using the mass size, I'm going to use this well-behaved, slow evolution, sigma-1 mass relation. And I'm going to do the same using the distance from the quiescent relation here, because that's ultimately where all the star-forming galaxies are going to go when they quench, because we know that all quiescent galaxies have dense cores. So now I construct this delta-delta diagram, and you can see, again, we have this L-shaped diagram. It looks very similar at all redshifts, and in fact, the normalization of this diagram evolves very little with time compared, for example, to the evolution that I showed in the mass size diagram. So the sizes of galaxies, both the star-forming and quiescent, evolve a lot. Their density in the central 1 kpc, not so much. So in fact, using just a single threshold, you could actually select most of these quiescent galaxies at any redshift, and also these compact star-forming galaxies that will be the most likely progenitor. So just like I did at the beginning, this will correspond to the first diagram that I showed you at redshift 2. This will be the compact star-forming galaxies at redshift 2, that they're very round and small galaxies that look a lot like the quiescent galaxies. But you can have the same L-shaped evolution at lower redshift, and this probably will be these galaxies with denser cores. But essentially, you have the same L-shaped diagram that summarizes this evolution, and it essentially summarizes 2 key steps. This would be the evolution along the star-forming and structural main sequence. Then you will have a compaction event that can be of many different kinds, because the strength of these compaction events change with time, that essentially will make the galaxy profile more concentrated, and then galaxies will quench, moving down in the star formation rate once they reach the maximum central density. So the structural transformation happens first, and just like you can stack all of these diagrams in redshift 3 down to redshift 0.5, and you get this universal L-shape. So all galaxies, even though their structural properties may be different and star formation rates may be different, follow the same sequence in which they build up their central density before quenching. And this is my takeaway slide. Just I was saying, this is our previous result at redshift 2 based on the effective surface density using the effective radius. And here's the stack evolution at every redshift, which is less dependent of the evolution of the 0 point, and again summarizes the same idea at every redshift. Galaxies become compact before quenching star formation. And I think I still have 2 minutes, or 1.
You have about a minute.
Okay, so this is my takeaway slide. I didn't know if I was going to have time, but I couldn't resist showing these nice postage stamps. So this will be very similar to the redshift 2 evolution that I was showing you here. So extended galaxies, compact star-forming galaxies, and quench galaxies. And what I was showing before is that you have the same L-shaped evolution, but the properties of galaxies are very different. So compact star-forming galaxies at redshift 2 are just naked cores. At lower redshift, you have just star-forming galaxies with dense cores that are going to quench into very similar quiescent galaxies. But the same ideas remain in this L-shape. And here just show the growing mass as a function of time. So you can actually, grabbing galaxies from these different evolutionary stages, you can even see an evolution along the main sequence in a structure as a function of time, and galaxies that depart from this sequence due to compaction and become quiescent at different times. So if you only know the growth in size, you can eventually turn into these other evolutionary phases at any time. So any galaxy starting here could end up here following different evolutionary tracks. But first they will compactify, they will become dense in the core, and then they will quench. Thank you.
Thank you. All right, time for questions.
Guillermo, first, thank you for this lovely talk. I just wanted to point out one thing and then make a comment. We actually find the same identical results, as you may know, on the Dakel et al. 2015, which was on Science. So we were seeing the structural sequence as you are showing, and the other lovely data observational results that you have, but we were only having 35 galaxies.
Yes,
it's lovely to see it on the big sample. What we seem to differ, in a sense, is just the last step of the interpretation, because I get the impression that you don't fold in progenitor bias, and so you read a sort of evolutionary sequence on what seems to be one snapshot of time. Maybe I'm getting this not completely wrong, but it's one of the issues that I would love to raise for a discussion, because the point is that the data, there is no disagreement at all on what they're doing, but there is the possibility indeed, and maybe I will show it later on one slide, that what we are seeing is actually straight down quenching from the main sequence, and that this red nugget cores, which may well end up only in the very massive objects, which we know must have accreted dissipation.
I would say two things. First, you are completely correct. So every time I show this, it's a snapshot. So that's why I have this other diagram where actually you have galaxies growing in mass here, following some evolutionary tracks from, in this case, hydrodynamical simulation. So galaxies don't follow this evolution in a given fixed mass. They grow in mass. So they will go from here to here to here to here, or they compactify and follow the other track. So this includes this evolution in mass. They don't move along this L shape in a given snapshot. They grow in mass, but you don't really know at what time they have a compaction. So they could remain in the main sequence in a structure for a longer period of time. They can compactify earlier. And in fact, I have another one in which they can compactify even earlier and give you these compact blue nuggets. So that is true. And also another point about the evolution in this sequence that was also shown in Sandra's paper that was really fantastic is that we know that this evolution moves very little, but I seem to remember that you compared the position of the galaxies with the Fang et al. Relation at redshift 0. So that relation is slightly below that. So those galaxies actually have dense cores, but they're not quite there at the Quiescent relation at that redshift, I think.
But if I have 1 millisecond, no.
I want to get in one more question, so.
Well, maybe I missed it. Maybe you said it, but I'm trying to get a feel of what is the number density of these objects. You know.
Of which ones?
Well, the red nuggets are there, or the compact phase.
So yeah. So the sample is complete. What I was trying to do here is come up with an evolutionary sequence that allows you to follow Quiescent galaxies at every time without having to split it in compact, ultra compact, mega compact. So they grow in size. So unless you know how they grow in size, if you put a constant threshold in size, you will miss the sample with being complete. You will either get the most compact or the biggest one. If you look at their central density, you will get all of them, all of the Quiescent galaxies at every redshift. But you have to know that their sizes changes with time. So their properties evolve.
Thank you.